Hello, everyone. This is Angelo Corsaro. I'm CTO at ADLink and the lead of the Eclipse Cyclone project, the Eclipse Zenoh project. So what I'm going to discuss today, it's about the theory of everything, which is something we've tried to achieve over the past few years, and a goal that in a way was representing almost an holy grail for us, because we've always struggled with the problem of unifying data in motion and data at rest. In this presentation, we'll try to understand how actually we managed to do that. But before getting into the solution, let's try to understand a little bit better what is the problem. So in order to understand the problem, let's imagine for a moment that we are data, and let's see what happens to data typically in an information system. So data is produced, and then in order to do anything with it or something with it, this data has to be distributed. And usually we distribute the data, and where distribution could be inside a board, inside a local area network, or across the internet, really doesn't matter. But it's the act of distribution for doing what? Perhaps for computing. So computing upon this data, and eventually doing something with the result of this computation, and or store this data. But once we've completed our computation, then at some point, we are going to distribute again the result of this computation, or even if you've stored the data, then at some point we might want to retrieve the result, this information or this data out of the storages. And so we assume again, in moving this data around, computing over it, perhaps storing it again, and so on and so forth. So if we look now at the technological landscape, then the technologies for dealing with data at rest and data in motion really belong historically to two different families. So publish-subscribe has imposed itself as the leading paradigm for dealing with data in motion, while databases, let them be relational or NoSQL databases, have become the standard de facto or leading paradigm for dealing with data at rest. Again, it's always data, right? But we have two different technology already for moving data and storing data, which sounds reasonable. But let's see where this leads. So besides having PubSub for data in motion and databases for data at rest, there is another difference that is inherent to some of this technology, or the vast majority of this technology, is that data in motion usually is pushed to interested parties. So you have data production, and then there is some distribution technology that pushes this data to interested parties. While when data is at rest, we have to go and pull the data out of some store. Okay. Now, something else that I would like you to ponder upon, or something else I would like to point out, is that while mainstream solutions for data in motion enjoy location transparency. What do I mean with location transparency? Location transparency is a very important property if you want to build distributed systems at scale, that ensures that if I'm interested in some data, again, data in movement, I don't need to know where the source is located or how many sources there are for that data. The only things I need to do is to express my interest for the data, and then the infrastructure will take care of delivering the data to me. So this is very important properties that I think we have now taken the habit to exploit and enjoy in those technologies that indeed are used for data in motion. But if you look at the technology used for data at rest, they are location aware. So if I need to query a database, well, actually, I need to know where the database is. And you might be wondering, why is that strange? Well, why isn't it? Because if you think about it, it's always data. And we have managed to have location transparency in data in movement, but we do not have location transparency or the degree of location transparency that we need for data at rest. And this makes it very hard, actually, to then decentralize or have massive decentralization of storages, because if you do not have location transparency and you need to know where the data is stored, I mean, things get very complicated. So this obviously has introduced, a real technological fragmentation between the technology used to distribute data, technology that are used to store data, and again, another aspect, is the push-pull aspect that we just mentioned before. Now, if we go one step further and we consider the emergence of edge computing and the availability of compute, storage, and communication more and more toward the periphery of the system, and the increasing need of a large class of application of being able to compute and store much closer to where the data is created. Now you understand that all of a sudden we have necessity to keep data as local as possible and as decentralized as possible, but that necessity then strikes with the technological landscape, because as soon as we do that, since we do not have location transparency for that at rest, how am I going to retrieve the data? I mean, it becomes a very hairy and let's say not so nice to deal with engineering problem. Okay, because all of a sudden, I need to either build a layer of indexing, and then how about failure? How about replication? How do I do load balancing? I mean, things get very messy very quickly. And so we have been struggling with this problem for years. Our customer, we're struggling with this problem for years. And so we have tried to come up and try to identify the minimal set of primitives that can really allow us to deal with data, whether it's in motion or at rest, with full location transparency and at any scale. Okay, so this is what we would like to do. And just to give you some other example, robotics is a hot topic in these days because of either actual robots or autonomous vehicles or AGV and so on and so forth. But you look at the difference between the robotics application that they are trying to build going forward versus the robotics application that we were building thus far. They are very different, because more and more nowadays, we need to be able to deal with swarm robotics, with internet scale management and teleoperation. And again, if I have robots that are battery powered and I need to teleoperate or manage across the internet, well, keeping in mind that communication and I/O is what consumes the most battery, I have to be very careful in deciding, if I use a cloud-centric architecture, what I push back to a cloud versus what I keep on the robot, and then eventually I go and fetch straight from the robot, as if the robot was becoming also my data store. Okay, or at least that could be a design decision or a deployment decision, and so on and so forth. But again, the environment is far more dynamic, far more geo-distributed, and extremely different from what we were used with, in which a robot, up to a few years ago, was visualized as a robotic arm that you were using to do in an assembly line, which was typically one robot. It was fixed, very well geolocalized, standalone. It would communicate at land scale, and if you want to do any kind of teleoperation, it would be perfectly fine to do it through a cloud-centric architecture, because you have a local area network, you have proper power, and you are not moving around. Okay. So in order to fill this gap, as I said before, we decided to start from zero and say, okay, so if we were to address this problem and come up with a technology that allow us, in the most axiomatic manner to deal with data at rest and data in motion, how would this look like? So how can we actually come up with a minimal set of primitives and then make sure that we can implement these primitives both on a tiny embedded device, but also let them scale and run in extremely performant manner on high-end server. How can we scale up and down, but also at the same time, how can we design primitives that can easily scale out? Because again, systems that we need to deal with are inherently geo-distributed, and most of the time, internet scale. So all of these, reflections and innovations, and I would say creativity, was put together, shaped up a little bit. You add some mint, some ice, and what you get is essentially Zenoh. So as we will see, Zenoh is a technology stack that unifies data in motion, data at rest, as well as computation, okay, with only 4 primitives, which I'll explain in a moment. And again, it does that by blending very elegantly PubSub, okay, with geo-distributed queries in the tradition of named data networking. And we do that by having, an extremely good time and space efficiency. So as we will see in a couple of slides, our wire overhead is ridiculously low compared to many, or perhaps I would say any other technology, and especially if you compare the level of feature that we can provide. So before delving into the primitives, because I think that's the part where I want to spend more time on this presentation, let's look quickly at another unique feature of Zenoh. When we decide Zenoh, besides providing these high-level primitives that, as I said, we wanted to be able to implement also on very embedded devices, we also took another important decision. Our decision was, well, we want to be able for Zenoh to run at the data link layer. Why so? Well, because in some environment, and especially when you're running on constrained network, sometimes you can't afford the cost of IP. And we wanted to be able to run straight over data link. And in any case, as you will see, we have to do our routing. Our routers are software routers. I mean, could be implemented, portion of it could be implemented by hardware, but this is not what we do, nor we think is necessary for the kind of application we are targeting right now. But the key point is, in order to save bandwidth or to actually improve the already terrific performance that you'll see, we are able to actually sit on top of a data link, on top of a network, or on top of a transport. So in other terms, just to make a concrete example, we can run on a traditional IP stack, but we can run on top of Ethernet. We can run straight on top of Bluetooth, and so on and so forth. Okay, so what are the primitive abstractions that Zenoh provide? So first of all, how does Zenoh represent data? Zenoh represents data by means of resources, where resources are represented by a key and a value. A key has a structure like this string, okay, so home kitchen sensor temp, or home kitchen sensor CO2, C2O2. And by the way, something else to understand is that in order to retain very good wire efficiency, while as a programmer or as an architect or as a designer of your information model, you reason about resources and resource name, over the wire, we seldom send strings. Very often, these strings are encoded as very small integers, and where these integers are local to a session. So that means that you don't need, to be dealing with integer to save bandwidth. You don't have to be dealing with integer, more importantly, that are agreed at a global scale. You just use name, which is very natural for programmers, and then it is our runtime that does the proper tricks to map these strings to very small integers, typically just one byte integer, because they're bound to a session. And then again, it depends on the number of resources that your application uses. And ensure that whenever you send data, your data, as I mentioned before, has a ridiculously low wire overhead. This is important because if we were sending this string as part of each data sample, obviously we would have had an overhead in terms of data that was linear on the name of the resource, which is something we can't afford for some transport. I mean, think a transport like BLE or 802.15.4, where you have, in some cases, a few tens of bytes of MTU. That's just can't cut through it. So this is how you express resource name, which is how you name data. And then if you want to express an interest in a set of data or an intent in producing a set of data, then you can use key regular expression or key expression, as we call them. So for instance, home star sensor temp refer to any temperature sensor in my house, or home star C202 would actually expand to any number of layers or of levels separated by a forward slash. So with that in mind, how do you select data? Well, you select data using what we call selector, and a selector is composed by a key selector in which you identify the set of keys that you are interested on, and then you have a value selector. And in the value selector, you have a predicate, like, I want to know when the values, I'm only interested in the temperature sensor in any room in my home, only when the value is greater than 25. You can have projections also, like in the second case. So look, whenever the speed in my car is greater than 25, then project the acceleration. So I only want to have the acceleration field. And then we use the name of the data in order to route, as we will see, information both for data in movement as well as to route query when trying to retrieve data at rest. But we will see that in more details. Okay, what are the primitive endpoints that exist on a Zenoh network? Okay, first of all, as we mentioned before, there are resources. A resource is named data, so something like home kitchen sensor temp 21.5 Celsius. Then you have a publisher, and a publisher is just an optional declaration because we actually do not need you to explicitly declare publisher. But if you do, there are certain things that we can optimize. Likewise for resources, you don't need to declare resources, but if you do, there are some optimization that we can do eagerly. Otherwise, those optimization are done lazily. I don't have the time to explain the kind of optimization, but just to give you a hint, the optimization has to do with how much we can compact and how small of an integer we can use to represent your resource name. But anyway, so going back to the publisher, a publisher is nothing but a string of values for a key expression, and then you have a subscriber, which is a single value for a key expression. So a subscriber says, look, I'm interested in resources whose key matches this expression. And then we have this fourth abstraction, this fourth primitive, which is a queryable. You have to visualize a queryable, if we follow this analogy of water, like a well. A well is a place where you go with a saw to take water, right? And so what the queryable allow us to do is really represent endpoint that given a key, for a given key expression, make the promise that they will provide values whose key or resources whose key matches that key expression, okay? So what does this mean? Well, if we think a little bit more about it, if we have a queryable, and this queryable is just an endpoint that can appear anywhere on the network, and the only promise of this endpoint is, look, I am a queryable for this expression, then anything you look that matches this key expression, right, I can give you answer, okay? It's like an oracle. But again, a queryable doesn't tell you if the way in which you answer is by looking up data out of a storage or by computing the result or computing some result. So this primitive of a queryable allow us to express both the reading half of a database of a storage as well as a remote computation. And it's quite powerful because, as we will see then, we can provide abstraction of geo-distributed storage by combining some of these primitives, and we can map remote computation just as an implementation of a queryable, as we will see in a couple of slides. Okay, what are now the primitive operation? Well, you can scout. A scout is really has to be thought like a way of looking around, okay? So, and the way the scouting is a pluggable sub-protocol of Zenoh that also depends on the network you are on, because if you're running on Bluetooth versus an IP network or a cellular network, we might scout differently, okay? But the scout is just saying, okay, so who is around and how can I find an entry point to start then discovering the rest of the system and understanding how I can communicate. Then you have open close to actually establish a Zenoh session and negotiate all a series of parameters for the protocol. Some of the things that we can negotiate during session establishment, for instance, is the resolution of a sequence number. And why do we do that? Because actually there is no sequence number that works for any transport. If you're running on BLE, you want to use a very small sequence number. If you're running over a satellite link, you want to use a relatively large resolution for sequence number because you want to have lots of messages in flight without suffering the rollover. Then you can declare and undeclare the various entity we saw before, so resources, publisher, subscriber, as well as queryable. You can put a new value for a key expression. You can get the result for a query. And again, so there you're asking for data, okay? And where this data is sitting, you really don't care, as we will see, is the infrastructure that figures that out and runs the distributed query and consolidate the data back for you. And then in case in which you are a subscriber, a special subscriber, there is a pool subscriber. And as we will see, this is useful for subscribers that go under duty cycle or sleep. You can also pull data. So if you declare yourself as a pool subscriber, data won't be pushed to you, but as we will see, will be kept as close as possible to you, so that when you wake up or when you're ready to consume the data, you say to Zenoh, pull and Zenoh will deliver you the data. You can also decide with which space you want to pull. You can say, look, I want to pull 1 sample, 2 sample, 10 sample, or the sample that are available for me. And it's the infrastructure that eventually will cache that. So these are all the primitives that in terms of operation and abstraction that we have in Zenoh. So as you see, we have 4 abstraction and actually less than 10 primitive operations. But we have also some derived abstraction. The most notable example is a storage. So a storage is defined by means of a selector that defines a set of resources that that this storage will store and for which it will answer a query, in other terms, and a backend, where a backend is essentially implemented by means of a plugin. So you can implement your own storage backend. As of today, we have storage backend plugin for RocksDB, InfluxDB, MariaDB, file system, main memory, you name it. And any other can be added quite easily. And then actually, as an implementation, as we will see, a storage is really mapped into the reading half, which is a queryable, and the writing half, which is a subscriber. Okay, because whenever data is a new resource is updated, you really want the storage to be updated also. Storage align, although that's not yet implemented, okay, in our roadmap there are also support for quorums, because the default consistency model for Zenoh is eventual consistency. In fact, strong eventual consistency. But for those that require strong consistency, we will make it possible for storage to support quorums, read and write quorums. But again, I don't have the time to explain in details. Perhaps we'll dedicate some later presentation on consistency model and how we do quorums, and how actually the same mechanism that we use to do quorums is used to do things that looks like MapReduce. But anyway. Then we have an eval. What is an eval? Well, an eval, or an evaluation, like a remote computation, for those of you that know Linda, obviously this is inspired from Linda in a way. An eval is nothing but a queryable that has associated a user-defined computation. The user-defined computation can be expressed in your favorite programming language, because this runs in userland, doesn't run in the infrastructure. The infrastructure just brings the request for the computation to the computation, but then it is the user code that actually runs or execute the eval. It has a selector that defines a set of resource keys that will trigger this computation, and then the implementation, which, as I mentioned, is provided by the user, either in Rust, which is the language in which we wrote Zenoh and our favorite language, or any of the supported language, so Python, C, C++, C#, and so on and so forth. So here you see how the non-primitive abstraction are mapped on top of primitive abstraction, as I mentioned before. And let's move quickly to communication topologies. So now we have the abstraction, right? You know that we can have storages that are anywhere, and through a GET, we actually get to query the storages. But what are the kind of topologies that we support? So in Zenoh, we support peer-to-peer communication. And for peer-to-peer, you can have a peer-to-peer over a click, so a fully connected graph, or an arbitrary mesh. And we use that both with some ad hoc network as well as over wide geographical area, where it doesn't really make sense to have everyone talking with everyone else. We can have routed communication. So if you have some nodes that are constrained, again, we both, as we will see, we have an implementation that really runs on small devices, but then an implementation can run as a client, which means that it doesn't communicate directly with any other user application. Okay, so its communication needs to be mediated either by Zenoh router or by Zenoh peer. And we have some application in which, for instance, we have little drone ships for ocean exploration that communicate through a mesh peer-to-peer. And then there are even smaller ships that are in a client role and communicate with any of the closest peer. And then it's the peer that actually meshes through the communication, either with the rest of the system that sits on the other side of the world, potentially, or with other small robots that are perhaps a client whose communication is mediated by yet another peer. So in terms of the most generic topology that we support, You can have routers, you can have peers, you can have clients, and you can mix and match all of these as you want. So when would you use this kind of topology? Well, routers usually are deployed at an infrastructural level. So we have, for instance, a 24/7 running infrastructure with routers deployed in Europe, Asia, and US. And for instance, imagine I have a swarm of robots or some application that are communicating peer-to-peer in a city or in a building, right? So they would do peer-to-peer and then be teleoperated by an operator that sits, maybe not in Paris where I'm sitting, but perhaps that sits in London or in New York, teleoperated by Zenoh. And in that case, the Zenoh communication would go through our backbone routers, okay? But in any case, you can mix and match this at will. But there is something else that we need to deal with. So I've mentioned several times things that moves, right? And there are things that move, but just move a little bit. And there are things that move like car or trains that move fast and can move by a lot. So imagine for a moment that I'm in Paris and I decide to go in Oslo, okay? So I turn on my car in Paris and I start driving without stopping, going toward Oslo. So if my car was doing V2X through Zenoh, as actually that's one of the use case, when I start, I will initiate a session with one of the Zenoh infrastructural road that is in Paris. And although my radio session will, especially if I'm communicating through a cellular network, will be migrating through different infrastructure node, perhaps my actual Zenoh session wouldn't be migrating. And so I would still communicating through Paris. And this communication would then, be forwarded through our routing infrastructure, let's say in Hamburg, if I'm then in Hamburg, okay, to communicate with another car that is just 100 meters away from me. And again, this is kind of silly, and this is why in Zenoh, we automatically migrate session. So in the case in which you have mobility, we have the ability to either detect changes in the physical layer connectivity and thus migrate session, as well as provide a management API that allow an infrastructure either automatically or by means of an operator to migrate session. And this is fundamental for mobility. Okay, this is also supported, and that's one of the rather unique feature that Zenoh supports. Okay, so let's put this all together. So as I'm in Paris, let's imagine for a moment to be at the Louvre Museum. And let's imagine that Louvre was using Zenoh and they wanted to keep the data for different sensor stored in storages that were kept on every floor of the Louvre. So here I'm just showing 2 floors. So Louvre 1 is the first floor, 42 is the number of the room, and then you have the kind of sensor. So in this case, whenever there is a publication from a sensor, all interested subscriber will receive the data as well as the storage whose key expression matches the resource that is being written, okay? Now, suppose there is another publication, and notice that at the bottom left, there is a subscriber, there is a pool subscriber. So this pool subscriber is sleeping, so it cannot receive data. In this case, it will be the Zenoh infrastructure that will keep the data, and whenever the pool subscriber wakes up, he asks Zenoh to give it the data. Zenoh will give the data and eventually garbage collect the retrieved data from the infrastructure. Now, suppose that now I'm interested in getting the temperature sensor for room 42 across all floor. So look here, we don't need to know how many databases there are, where are the databases. Look, this is completely location transparent. So an application or an administrator, anybody would submit this query. And then it's Zenoh that says, okay, let me find the minimal set and the optimal set of storages that cover this query. Okay, that's covered in terms of set theory. It will get there to the storage will execute the query, Zenoh will consolidate back the data and get you back the data, okay? And so this is how we get location transparency also for that at rest. And you don't care about the level of replication, okay, because you can replicate. You can replicate a different tier because I could have data in the Louvre, I could have data in a French data center, I could have data replicated in a European data center, and so on and so forth. And depending on where I am on the network, Zenoh will always try to get the data in the optimal manner. So this is super powerful. and it frees you from the detail of having to know where data is stored, which is a major hassle in in building systems that scale and systems that can exploit locality and can easily exploit load balancing and fault tolerance. So this is, I think, one of the very nice feature that Zenoh provides. Okay, so trying to quickly wrap up. So Zenoh provides you with very efficient protocol, okay, with connectivity to extremely constrained targets. It has a terrific wire efficiency. We have between 4 to 6 bytes of overhead for data. We support QoS, so we can differentiate traffic and do data prioritization. We support zero copy, and as you saw, we have a large set of APIs supported, which I will quickly report here. We also run on very small devices. I mean, you will see the cute Zenoh Pico logo, and the number of devices that we support is roughly open-ended. So who is this? Who is using this? Well, it's being used on a wide set of application domains, and that you can see here. But I just want to show you the latest example that or use case that got the press. We were used as part of the the India Autonomous Challenge. You see the cute logo on the car there, and we were used to power the V2X. Okay, and we were running on a curb, so this is called a reliable backhaul, where every car had 1 megabit per second, and we were constrained not to send more than 140 UDP packet per second. Okay, so I'll conclude my presentation here.